So today we're going to continue where we left off in our goal to compute scattering cross-sections and decay rates. So yesterday we did part of the, went part of the way there. We related cross-sections and decay rates to scattering amplitudes. And today we're going to continue that journey and relate. Our main result today will be a relationship between these scattering amplitudes and time-ordered expectation values of interacting fields. Which is closer to something we know how to compute. So in the second lecture, we saw that we could compute these time-ordered expectation values for two fields in a free theory, and that's where we'll go tomorrow. So tomorrow, we'll then relate these to time-ordered expectation values in a free theory. And actually be able to, from start to finish, compute a scattering amplitude. So this step was yesterday, this step will be today, this step is tomorrow. And so this part is today. And in order to relate these scattering amplitudes to time-ordered vacuum expectation values of fields, we're going to need to make a few assumptions. I'll state those now, and we'll then derive a relation, and in the second part of lecture, we'll examine those assumptions. We'll be able to make these assumptions work, but at the cost of having to modify our theory in a way I'll describe in the later part of lecture. So the assumptions we're going to make are first that our creation and annihilation operators work the same way in the interacting theory as they do in the free theory, apart from their time evolution. So in particular, we'll assume that the creation operator in an interacting theory, it'll in general be time dependent. This will create a particle with momentum p at time t. There should be some operator that does that, and we'll just call that our creation operator. Furthermore, so we'll assume that the annihilation operator does the same thing. It annihilates the particle with momentum e at time t. And we'll assume that at any fixed time, our commutation relations are the same. As in the free theory. Okay. So in a sense, we could just take this as a definition of some operators in the interacting theory. So in a sense, these are just definitions of what we mean by a p dagger and AP. Another assumption we're going to make is that this is still a one-particle state in the interacting theory with the same form factor. So we'll assume that this is a one particle state. With the same form factor that you computed in the tutorial, which was p phi of x omega is e to the I b dot x. Okay. So we'll make that assumption. Be necessary to derive something like this. So we're going to relate our initial and final states will be in momentum space. Usually we're interested in momentum scattering, momentum eigenstates, or at least initial and final particles, which are highly localized in momentum space. And over here, we've got an expression in position space. So we need to be able to relate those two. So with these assumptions, this tells us that the relationship between the field operator and the ladder operators should be the same as it is in the free theory. So in particular, if this is a one particle state and AP dagger creates a one particle state when we act with it on the vacuum, then phi should be linear in AP dagger. So it should be something like this. We'll have a term AP dagger of t. Has to be linear if we want it to be a one particle state. The coefficient needs to be e to the I p dot x if we want the form factor to be correct. If we changed this factor, we would modify this relation. And if we want it to be a real field, then we should have the other term that we're used to, the same annihilation operator, times e to the minus I p dot x. So if we have these assumptions. The relationship between the ladder operators and the field operators is the same as in the free theory. The only difference between the free theory and the interacting theory is the time dependence, which we could, if we were given a Hamiltonian, we could figure that out from the Heisenberg equation of motion. That's generally difficult to do in practice, at least exactly. Sometimes do that perturbatively, but we won't need any explicit time dependence. All we'll use is basically that we have the same relationship between the field and the ladder operators as in the free theory. And if we have this relationship between the field operators and the ladder operators, we can invert it, just like you did in tutorial 1. And we'll also need to go backwards. So you inverted that relationship and found that we can write the ladder operator in terms of the minus I here, field operators like this. And so we'll also use this. Okay. So in essence, we're assuming the only difference between the free theory and the interacting theory is in the time dependence of the ladder operators. So in the free theory, the same ladder operator, same creation operator creates a momentum state p at any time, the operators that create a given momentum state will change with time in the interacting theory. Okay. So we'll come back at the end of the lecture to look at whether these assumptions are consistent. But for now, we'll just assume them. And for simplicity, we'll derive the LSZ reduction formula for the simplest interesting case, which is 2 to 2 scattering. So let's consider 2 to 2 scattering. And then we can consider an initial state at time minus infinity to be just a state where we have two particles of momentum k1 and k2. And I'll abbreviate this. Instead of writing a sub k sub 1 every time, I'll just write this as a1 dagger minus infinity, a2 dagger minus infinity. So that's an initial state with two particles in the far past. Our final state in the far future will be the same kind of thing. Let's call the momentum of our the particles in the final state to be K3 and K4. And this will be our final state. Any questions so far? So the most of the work in deriving the LSZ reduction formula will involve using this useful identity, which relates the creation operators or annihilation operators in the far past and the far future. So the difference between the creation operators in the future and the past is given by this formula. And I'll call the right-hand side of this I1 dagger. So I'll derive this in a minute. But so here we've got a relationship between the creation operators in the future and the past, and it's related to the field operators, which is what we want to do if we're going to relate our scattering cross-section, which is in terms of momentum eigenstates, in terms of the ladder operators in the far past and far future, and our field operators. We're going to get a time-ordered expectation value related to our field operators. Here we've got the Klein-Gordon operator acting on our field. This would be 0. Well, Klein-Gordon equation says that this is 0 if we've got a free theory. But we're looking at an interacting theory. So our equation of motion will have additional terms. And equation of motion will be something different other than this Klein-Gordon operator acting in the field is 0. So where does this come from? it over here. So, simple thing we can do is we can write this difference in these operators as just an integral of a derivative. So this is the integral dt of time derivative of a1 of t. And now we can use our assumption that we have this same relationship between our field operators and our ladder operators in this form. So we can invert this relation to get a relationship between the creation operator and the field operators. So let's use that now. And we get, we already have an integral over time in that relationship between the creation operator and the field operator. We've got an integral over space. So we can combine those to be an integral over space-time. And then we've got the derivative of e to the minus I k1 x, derivative of phi I ek1 phi. Okay. And we can evaluate this time derivative at 4 terms. So we get a minus I ek1 times, well, everything is going to have a, I'll write this first. We take the derivative on here, we get a minus I ek1 times this. And then we also get plus 2 derivatives on phi and plus I ek1 derivative of phi. And the first and last terms cancel. I've got exactly the same thing. And so we're just left with these 2 terms, which we can write as minus I d4x. We just expand out the energy. You can write this as k squared plus m squared. And we can write the integral of e to the minus I k dot x of k squared 5x squared. So this is the integral of, we act with the gradient squared on e to the I minus I k dot x times 5x. And then we can take, for this term, we can then integrate by parts twice and assume our boundary terms are 0. Move this derivative from the exponential onto the field. Then we get this integral minus sign here. Minus, because we bring down an I squared. Which is exactly what we wanted. We can combine these two derivatives into the 4 derivatives squared. So this is exactly what we wanted. Any questions there? Yes.
I don't see why it should be a minus squared, because you got a minus over there and then you integrated by parts again, so it became a plus.
We integrated by parts twice.
Oh.
We get 2 minus signs. Okay. And exactly the same thing holds. If we just conjugate everything, we can get a relationship between the annihilation operators in the far future and the annihilation operators in the far past. And that gives us I1, which is just the same thing conjugated. And so we can then use these identities and plug them into our expression for the scattering amplitude. And we get, so this is A4 plus infinity, 3 of plus infinity, A1 minus infinity, 2 of minus infinity, omega, which is already time ordered. So I'm just going to throw in a time ordering symbol. And then I can use our useful identity. So we'll use A1 plus infinity minus A1 of minus infinity. Should be daggers here. So we want to relate the creation operator in the far past to the creation operator in the far future. So this creation operator in the far past is the creation operator in the far future minus I1 dagger. And the annihilation operator, all of our annihilation operators in the far future, those are related to the annihilation operators in the far past by adding this integral. Yes.
Where did the S minus 1 go?
Okay, so we're considering these states are states in the far past or the far future. So we can think about these as being like Schrodinger picture versus Heisenberg, which is, I should probably write this as I of minus infinity to indicate that these are slightly different from the, here this is the Heisenberg picture, over here I'm in the Schrodinger picture. Yes?
And why? What happened to the S?
So this if we're in so there's a relationship between F S I in the Heisenberg picture is some state in the far future in the Schrodinger picture with some state in the inner product in the Schrodinger picture. So here I'm considering just states in the far past and far future in the Schrodinger picture, which are related to this picture. So, sorry for, I shouldn't have used the same notation.
Don't you need to evolve the initial state to infinity before you can act on it from the left?
These are the same things. So this state is time independent, and here the time evolution is in this operator. Over here, the time evolution is in, well, we're considering states at different times. So that's what we're doing over here. We're considering states defined at different times.
So we don't know the I and F in the Heisenberg structures.
Right. We won't need those.
Why is it minus identity?
We're just considering this. So far, it doesn't really matter, but we're only going to be interested in the case where the initial state's different from the final state. There'll be there'll be a slight subtlety if we consider the initial state to be the same as the final state, which I don't want to deal with. So we'll throw away the uninteresting case where there's no scattering.
But it seems to me that it should be just FSI. Because
It so far, yeah, sure.
you mean they are the same?
We can consider them separately. So there's if we're interested in scattering, if we do a scattering experiment, we send in some particles. Will be some probability that they miss each other, and the final state's equal to the initial state. No scattering, or they could interact, and the final state could be different from the initial state. Those two cases are both easy to distinguish experimentally, and they never interfere quantum mechanically, so we can treat them entirely separately. So
Okay,
I'm
final state and initial state, the inner product of final state and initial state is 0?
No. The final state is different. Oh, yes. So we're assuming that the final state is different from the initial state. So if we consider them at the same time, we look at f at minus infinity and I at minus infinity, that would be 0. They're different.
Just to be sure I understand, can you please write the definition of your Heisenberg states in terms of the creation operators?
Well, so the Heisenberg picture should be the same as the Schrodinger picture at some fixed time. You could choose that to be, say, minus infinity, in which case this would be the same. But then we would need to time evolve this backwards. So then this would, F would be the time evolution operator from of F minus infinity. So we need to evolve it from infinity to minus infinity, where this is just some time evolution. or we could compare them at some other time, in which case we would need to evolve both of those states. Okay. So we can take our amplitude, note that it's already time ordered, and then use this useful identity. And what we get, well, will be 2 to the 4th terms. Fortunately, most of them will be 0. So what we'll get will be terms like a4 of minus infinity, a3 of minus infinity, a1 dagger of plus infinity, a2 dagger plus infinity, omega plus a whole bunch of other terms that involve some combination of ladder operators and these integrals. They're called I. And we'll get one term that has no ladder operators. Okay, so let's look at this first term. So this first term has, I put the, okay, yep, that's correct. Yeah, so we need to time order this. So if we time order this, the annihilation operators will move to the right, where they'll annihilate the vacuum, and the creation operators will move to the left, where they'll annihilate the Brava vacuum. So this term is 0. After time ordering, we've got annihilation operators acting on the Ket vacuum and creation operators acting on the Brava vacuum. So this term is 0. So are all the other terms I didn't write, which have at least one creation operator or at least one annihilation operator. So these operators are either all the creation operators are acting at plus infinity, so time ordering will bring all the creation operators to the far left, where they'll annihilate the Brava vacuum, and the annihilation operators will all be brought to the far right, because they're in the far past, the asymptotic past, where they'll annihilate the Ket vacuum. So as long as there's at least one annihilation or creation operator, all these terms are 0. So the only term that survives is this last one. And so that so we've derived what we want, which is a relationship between the scattering amplitude and a time-ordered product of fields. All these i's involve fields. So let me just rewrite that term a little more explicitly to give us the LSZ reduction formula. And I'm just by hand, again, throwing away the case where there's no scattering. Treat it separately. So we get one factor of I from each of these. So we've got minus, so in this formula, well, these should both have a minus sign. I've canceled off that minus sign, so minus I, one dagger has a plus I. So does I without a dagger. Then we need to we've got a product over all of our particles. So each of the integrals I has an integral over spacetime. Then we've got an exponential factor. which can have either a plus sign or a minus sign in the exponent, depending on whether it's an eye or an eye dagger. So here, lambda j is +1 for initial states, initial particles, and -1 for final particles. So the eye dagger, we've got a minus sign, and the exponent, and so that means we should have lambda j equal to 1. I pulled out the minus sign here. And for the states in the particles in the final state, should have a plus sign in the exponent. We then have a Klein-Gordon operator. For each of the fields. So here by delta j squared, I mean eta mu nu d x mu j d x nu j. And this is all acting on a time-ordered product of fields. So here, by phi I mean phi of xi. This is a shorthand notation I'll be using frequently throughout the course. So this is the key result of today's lecture. This is the LSZ reduction formula. And what's it telling us? It's telling us that if we've got scattering amplitude, well, what we need to do is we need to compute a time-ordered correlation function, act with Klein-Gordon operators for each of the particles in our external state. We're going to see that these, so eventually we're going to relate this to the Feynman propagator from the first lecture, and that's a Green's function of this operator. So basically what this operator is going to do is it's going to remove a propagator for our external states, and then we need to Fourier transform. The sign depends on whether our particles are in the past or future. Any questions on that? So, yes.
2 plus 2? Like, is that just
So basically our entire derivation works if we have more particles in our final state or a different number of particles in our initial state. And the only thing that would really change in this formula is we'd get more factors of I, we'd have more integrals, and we'd have more particles, more fields here. Okay. Yes.
So, do we have any good motivation to take these assumptions in the case where we don't have a free Lagrangian?
Okay, so we can, the first two, those assumptions about the ladder operators, we can take those as basically definition. There should be some operators that add or remove particles. The last one, well, that would be a nice interpretation, and I'm about to discuss that in some more detail. So, yeah, I've got a lot to say about that, but that's the next part of class. in a few words, we expect that there's some operator that creates a one particle state that's localized in position space, and it's just a nice interpretation to call that the field operator. So that's a few word explanation, but that's we're going to re-examine these assumptions. Okay, so perhaps we made a few assumptions at the beginning. Our assumptions about the ladder operators we can take as definitions. The assumptions about the field operator are perhaps a bit more questionable, so I'd like to examine those. So what did we assume? We assumed that phi x is a one-particle state, with the usual form factor. And so what do we mean if we say that this is a one-particle state? So that means a few things. So one thing it means if we call this a one-particle state is that a one-particle state should be different from zero-particle states, and our zero-particle state is the vacuum state. So if I call this a one-particle state, it certainly should be true that the overlap of this one-particle state with the vacuum state is 0. So that's part of what I mean when I say that this is a one-particle state, is that it's different from the vacuum state. And, well, I explicitly assumed that, well, this is a one-particle state, and this is a choice of normalization of our one-particle. If it is a one-particle state, this is a statement about how this one-particle state is normalized. So we'll examine that statement also. And one-particle state should also be different from multi-particle states. So that's the last thing we should check. So we should be able to distinguish one particle and multi-particle states. And I won't write an equation for this one yet. We'll come back to that when we consider this point. So I just like to consider each of these points one at a time to see whether they're reasonable assumptions or whether we can make them work in general. And what we're going to find is that we can make these two assumptions work if we're willing to modify our theory. And basically, these two assumptions are going to force us to renormalize our theory. This last one is a bit different from the first two, and this one can work, but we'll see there's some subtleties there. Okay, so our first thing we need to check is, or examine, is what can we say about this one-point function? Without specifying a theory, there's not a lot we can do. Well, one thing we can do is we can write our field in terms of a translated version of the field, or translated, where E mu is the zeroth component is the Hamiltonian, and the other three components are the momentum operator. So if we were going back and forth between the Heisenberg picture and the Schrodinger picture, we'd just act with exponential of IHT on, or minus IHT on either side. That basically translates our operator in time, and we can do the same thing to do a Four translation. And so one thing we can do is we can write, use this translation to write phi of x, the expectation value of phi of x, as omega e to the I p dot x to the minus I p dot x. And if we translate the vacuum, we just get back the vacuum because we assume that our vacuum is Lorentz and Poincare invariant. Be 0. So we get back and there's not much else we can say about this. This is a Lorentz invariant number. It doesn't depend on, it doesn't transform if we do a Lorentz transformation. But there's absolutely no reason to expect it to be 0. And I can give you dozens of examples where you can compute this, and this is not 0. So this is non-zero in general. We can say it is a Lorentz invariant number, which we can call V. Okay, so our very first assumption, or our assumption in deriving the LSZ formula, doesn't seem to work. That would be extremely problematic if we couldn't fix it, because, well, basically we're going to need to use the LSZ formula to do perturbation theory. And in most cases, we can't compute things exactly, and perturbation theory is our only technique. And basically, all of the usual versions of perturbation theory I know of rely on the LSZ formula. So we better be able to fix this, or we're in a lot of trouble. Fortunately, we can fix this rather easily just by redefining our field operators. So if we define a new field operator to be phi tilde of x, which is just phi of x minus v, so just a shifted version of our field operator, then our new field operator will have 0 vacuum expectation value. This is known as the vacuum expectation value of the field. So so if you do this, then the vacuum expectation value, or VEV, of phi tilde is 0. And so we can, we found a new field, which is related to our original field, which has no vacuum excitation value, and so we can interpret this, at least so far consistent to interpret by tilde of x acting on omega as a one-particle state, because it's different from the zero-particle state. And so we can fix this. No matter what the VEV of our original field is, we can always shift things to give ourselves a new field, which at least potentially can create a one-particle state. And so from now on, we'll drop the tilde and just assume that we've shifted things so that our fields have zero VEV.
Where did we use this assumption in the LSZ formula?
I assumed that so I assumed that 5x was a one-particle state, the bottom of the board up there, which meant that the field operator had to be related to the ladder operators in this way. It should be linear in the creation operators, and the reality of this field tells us that then we should have to have the annihilation operator. That's where we used it.
And when you shift it by v, how do you know that it still looks like that? Like, how do you?
Well, we assumed it looked like that. So if we shifted it and it looked like that, it would no longer look like that.
I see.
Why do we want the vacuum Lorentz invariant?
The vacuum to be Lorentz invariant.
Scale.
So that's just I suppose in principle you could assume that the vacuum is non-Lorentz invariant, but we know a very good approximation that Lorentz invariance holds. So you'd probably run into a problem with experiments. It's another assumption. We're also assuming that the vacuum is Lorentz invariant. That's.
So do you want to?
I can add that to my list of assumptions if you like.
To check this assumption.
It's not an assumption we're going to check, but that is an assumption we're making.
Why?
Well, Lorentz invariance is extremely well tested experimentally. If the vacuum state was not Lorentz invariant, that would likely have experimental signatures, so it's pretty well constrained. There's probably room to have a small amount of violation of Lorentz invariance, but it's not easy to construct. It's not easy to construct a theory that violates Lorentz invariance and is consistent with experiment. You don't look happy with that, but I'll be happy to discuss more with you after lecture. If you like. Okay, so okay, so our next assumption was the assumption that the form factor takes the same form as in the free theory. And again, there's not a lot we can do without specifying the theory. We can, again, write 5x in terms of 5, 0. Together with the 4 translation operators. And so again, we're making the additional assumption, which I'm not going to justify any further, that the vacuum is Lorentz invariant and Poincare invariant. So translate the vacuum, we get back the vacuum. Over here, we've got a momentum eigenstate. So we will get a factor of e to the I k x k phi of 0 omega. And our choice of normalization of our states and operators has been chosen so that all of our amplitudes are Lorentz invariant. So this is a Lorentz invariant object. It depends only on k. So we only have a single vector that we can use to make a Lorentz invariant object, and the only way we can do that is by looking, taking k squared. So, and k squared will be m squared, the mass of particle in our in this one particle state. So this should be a function of m squared. And again, we want this to be 1 in order for the form factor to take the correct form. And again, there's absolutely no reason to expect this to be 1. So in general, it's some Lorentz invariant number, some function of the mass squared. But we don't know that this is equal to 1. Again, this is something we can fix rather easily. So we can fix this by rescaling. So if we take phi tilde of x to be some different normalization times x, phi of x, then we can set this constant to be 1, no matter what it is originally. So as long as we're willing to rescale our fields, we can make this assumption work. And again, we're going to drop the tilde from that one. So we can make our first two assumptions work as long as we're willing to shift and rescale our fields. Yes.
I have another question. I thought, maybe I'm wrong, that the momentum eigenstates were no longer energy eigenstates in the interaction theory.
So all of our external particles are particles in the asymptotic states in the far past and far future. The ones we'll measure will be on shell, so they'll satisfy the relationship k squared equals m squared. When we go to the, I think what you're referring to is when we go to the interaction picture and do perturbation theory, we're going to interpret scattering in terms of exchange of virtual particles where they don't satisfy that relation that k squared is m squared. So we haven't gotten there yet, but you're absolutely right that the particles in an interactive theory that are exchanged between our initial and final states, those will not satisfy k squared equals m squared. But this is an external particle, a physical particle that we can measure that should have the usual relationship between its energy and momentum.
Wait, why should the energy eigenstates be momentum eigenstates if you have interacting theory?
Well, if we measure a physical particle like an electron, all electrons have the same mass. And one way to think about what we mean by the mass is the mass tells us the relationship between the momentum and the energy. So if it's a measure the momentum, we know So we know the mass, we also know the energy. So they have to be simultaneous eigenstates. Or we wouldn't be able to say that electrons have a definite mass.
I mean, like, if you have a harmonic oscillator, the eigenstates are not eigenstates of momentum, right? In non-relativistic quantum mechanics. So what do you expect in relativistic quantum mechanics then?
My answer is we see these physical particles that have a definite mass. So that means that we measure the momentum, we know the energy. Maybe there's other ways to see it, but that's the way I think about it. Okay, so the last assumption we want to check is that we can distinguish multi-particle states from single particle states. Okay, so I'm going to denote my multi-particle states by their, I'll write them like P sigma, where P is the total 3 momentum. And sigma are all of the other parameters needed to describe the state. So this will include things like relative momenta between the various particles. We have particles of spin, specification of the spin of the particles, the number of particles, types of particles, everything else. This won't play a large role. What we really care about is just the total 3 momentum of our multi-particle state. And we can try to do the same thing as before. So it's certainly true we can distinguish a single particle state with a multi-particle state if we'd certainly be able to distinguish them if the inner product of P sigma, the overlap of P sigma with our one particle state phi of x omega was 0. We can do the same thing as before, and we get, just writing this in terms of translation. We get e to the I p dot x times e sigma I of 0 omega. And there's no reason to expect this to be 0. It's just some Lorentz invariant function of our momenta, which I'll call a sigma of P. And this is not 0. And there's nothing we can do to our field, nothing simple at least, we can do to our field to set this equal to 0. We've already shifted and rescaled. And this would be momentum and position dependent. So there's no easy way to make this 0. And that's perhaps not such a bad thing. We want to be able to describe things like the decay of a single particle. So I'd like there to be some way for a single particle state to transition into a multi-particle state. So this is too strong of a condition to impose, that this one particle state has no overlap with a general multi-particle state. We want there to be some overlap. But at the same time, we do want to be able to distinguish what we mean by a one-particle state and a multi-particle state. If we couldn't distinguish them, there's no sense in which a state is one particle or multi-particle. And so what we really want is to be able to distinguish one-particle states and multi-particle states in the asymptotic past or future, where we're imagining all our measurements are taking place. And so in order to see that we can distinguish our one-particle states and multi-particle states, we need to construct wave packets. So if we've got a multi-particle wave packet, we can write it as a sum and integral over sigma. So sigma will, in general, contain some continuous parameters like relative momenta and some discrete parameters like particle number times an integral of some wave packet times our multi-particle momentum eigenstate. So, and we can do the same thing for our one-particle states. So we can construct a one-particle wave packet, which is an integral of F1 K, A1 dagger T, omega. This is a multi-particle wave packet. And this is a single particle wave packet. And you can think of psi sigma and F1 of K as, for instance, being Gaussians. So, for instance, F1 of K could be a Gaussian like e to the minus K minus K1. Squared over some width. So this is, we describe a, and similarly for sigma, this would describe a particle that's localized both in position and momentum space, and in momentum space, it's localized near K1. There's some width, and so construct wave packets. And so these are normalizable states, unlike our momentum eigenstates or our position eigenstates. So these ones are normalizable, and so we won't run into any problems due to the using non-normalizable states. And so what we'd like is that the overlap between these two states goes to 0 as t goes to plus or minus infinity. If that's true, then we can at least distinguish a one-particle wave packet from a multi-particle wave packet in the far past or far future, where all of our measurements occur. And in that sense, so then we can make a statement about what we mean by a one-particle state. Any questions at this point? Yes.
Sorry, can you explain again why here the A depends on P, but over there it only depends on M?
Okay, so, well, in this case, in the case where we have a single particle state, the only possible thing, so we know our amplitude is Lorentz invariant, and it's a Lorentz invariant. K50 omega is a Lorentz invariant object that only can depend on K. So there's only one possible way to make a Lorentz invariant object out of a single 4 vector, which is square it, or, well, you can then have any function of the square of that, but it would be Lorentz invariant.
Okay.
Here we've got not only the 3 momentum, but inside sigma, there's hidden 4 vectors like relative momenta. So there's, in general, this would be some Lorentz invariant combination of whatever information is contained in that state. So we can't. So it'll depend on both sigma and p in some way.
Sigmas denote like how the momentum is distributed across the different particles or something?
Among other things. So sigma is everything else we need to describe the state besides the total 3 momentum. Yeah. So we can compute this overlap, and what we get is expression, plugging in our definitions. So what I've done here is I have just plugged in the definitions and then used the relationship between the ladder operator, the creation operator, A1 dagger, and the field operators, like we did before. So that's where these 5x's come from. And we note that this here, based on our previous calculation, is e to the I p dot x, a sigma p. And so this part in square brackets then becomes, if we take the derivative here, we get an I p naught. The derivative here gives us a 2 minus signs, so an I k naught, and e to the I p minus x, p minus k dot x, and sigma p. And then we can do the x integral. So the x integral will give us a delta p minus k. And then we can use that to do the k integral. So the net effect of doing both of these integrals will be to set k equal to p and multiply everything by 2 pi cubed. So then that gives us this expression. So we've got a whole bunch of factors which won't really matter. What's essential So we've got a P naught minus K naught in the exponent. So this part is basically irrelevant. All that matters really is we've got a P naught minus K naught in the exponent, and we also have, I guess, the 3 momentum part. No, we've done the 3. Done the x integral to get rid of the spatial part of this. Okay, and so P is the energy of the multiparticle state, and K is the energy of the single particle state. And these states have the same momentum because when we did the x integral, we got a delta E minus K. So x integral gives a delta E minus K. And so there's no bound states in our theory, then a multiparticle state should always have more energy than a single particle state with the same 3 momentum. You go to a frame where they're at rest, and then the energy of the single particle state should be m, and the energy of the multiparticle state should be at least 2m or more if there's no bound states. So P naught is greater than K naught because P is K. If we assume there's no bound states. And so this exponent is, it's a positive number times I, and in particular it's not 0. So if we take t going to infinity or minus infinity, this will oscillate more and more rapidly, and we'll get destructive interference, and this integral will go to 0. So this goes to 0 as t goes to plus or minus infinity due to destructive interference. Those of you who know what it is, it's essentially a consequence of the Riemann-Lebesgue lemma. So in this sense, we can distinguish one particle and multiparticle states. The overlap of any one particle state and any multiparticle state will go to 0 as t goes to plus or minus infinity, and that's where we do our measurements. So what this is saying in another way is that if we've got some multiparticle wave packet and some single particle wave packet, they'll spread out differently as we time evolve them, and the overlap will go to 0 in the far past or far future. So in that sense, we can distinguish multiparticle and single particle wave packets, and all we really need is that there are no bound states. This is even stronger than all we really need is there's no multiparticle states with the same energy or same mass as a single particle state in the center mass frame. So this is automatic. We need to modify our theory to satisfy the first 2 assumptions. This one is automatic. Well, with this small additional physical assumption. Any questions on that? Okay, so let me just let's just see what this means by looking at an example. Let's suppose we want to study scalar field theory, which has the Klein-Gordon terms plus an interaction term. Like this. So this is an interacting field theory. We've got a new term compared to our Klein-Gordon Lagrangian. And if we want to study this theory using perturbation theory, and to do perturbation theory, we have to use the LSZ formula. That's part of how we go from cross-sections down to the Feynman propagator. And we'll see where perturbation theory comes in tomorrow. But the key ingredient in doing perturbation theory is the LSZ reduction formula. And in order to use it, we have to, in general, shift and rescale our fields and rename them. So this will become, after we've shifted and rescaled our fields, we'll have we'll still have the same form of the kinetic term. So we'll get something like, but the a d phi squared term, but the coefficient will no longer be a half in general. So we'll get something like this. We'll still have a mass term, but the coefficient will no longer be a half. And we'll have the same interaction term. Coefficient will no longer be g over 3 factorial, zg times g. And if we shift this term, we take phi to phi minus v for a cubic term. We'll generate a cubic term, quadratic term, also a linear term in general. So we get a new term like y phi. So this is a new term. So not only will we change the coefficients, we'll in general introduce additional terms. And it's not, in general, consistent to do perturbation theory using this Lagrangian. We have to use this Lagrangian. So this is telling us that renormalization is required. It's not an option if you're doing perturbation theory. So we have to renormalize. Yes.
I was just going to ask, are these rescaling terms unique or not?
There in general would be relationships between these.
Okay.
I've just, for simplicity, just written them as independent coupling.
Okay.
So we'll, yes. Yeah. We'll come back to that topic in the what the relationships between these things are in my last lecture a little bit, and we'll learn how to compute these more explicitly in QFT2. So we won't go into the full details of how to actually do this renormalization in this course, but it's the things we're doing in this course force us to renormalize later. And for this course, we're mostly, apart from my last lecture, going to be interested in the leading order of perturbation theory, where it's okay to set all of these z's to 1 and y to 0. So in the leading order, it's consistent to set zi equals 1 and y equals 0 with this equals 0 and this equals e to the ikx. So this is typically consistent at leading order in perturbation theory. It's basically never consistent beyond leading order in perturbation theory. So for the next few lectures, we're going to just be working, or for the most part, be working at leading order. And so for the next few lectures, I'm going to set y to 0, any new terms we'd get to 0, and these changes in the coefficients to 1. It's okay to do that at leading order. It's not okay to do that beyond leading order. I'm going to do that just for notational simplicity, but you should keep in mind that once we go beyond leading order, we need to account for the fact that these coefficients change, and we sometimes get new terms. So and I'll have more to say about this next Wednesday. Okay, so to recap, we've seen how to relate FSI to time-ordered products of fields in the interacting theory. Yesterday, what we saw is we could relate the scattering amplitudes to cross sections and decay rates. And tomorrow, we'll see how to relate these endpoint functions in interacting theories to endpoint functions in free theories, where we know how to calculate them. We've calculated in a free theory the 2-point function. We did that in our discussion of the free Klein-Gordon theory. And we'll see it's not that much more difficult to compute time-ordered endpoint functions in free theories. And we'll do that tomorrow after we relate these time-ordered endpoint functions in the interacting theory to the time-ordered endpoint functions in the free theory. Are there any questions? Yes.
Is assumption on the non-existence of states that have the same energy, with particle states that have the same energy as one particle state, is really necessary? Or it can be removed if you do something more complicated?
There might be other ways to distinguish the states and that. But I'm not certain about that case. It's not a case I've looked at. If you have several different states with the same mass, you might be able to distinguish them by other properties of those states, for instance, charges. So I imagine you'd probably want to also call those other states one-particle states, but different one-particle state. So if you have a theory with multiple particles with the same mass, of course, there's not going to be a problem. But, I'm not aware of a context in which you'd call a state with the same mass as a one-particle state a multi-particle state.
So are you expanding in G over M, or what's the expansion parameter?
Our expansion parameter, yes, will typically be G or G over M or G over some energy scale. But, in this theory, G is dimensionful. We'll often look at theories where G is dimensionless. So in that case, it would just be the parameter. But yeah, in this case, we'd need a dimensionless parameter, which I guess could be G over M.
So does that mean like the interaction is, or like, what's the domain of validity for perturbation theory?
Okay, so many interacting field theories become either strongly coupled as you go to high energies, in which case you can't really do anything meaningful using perturbation theory to calculate scattering amplitudes, for instance. Typically there's a finite range in which you trust your theory, and there's some high energy cutoff. That's something we'll discuss in much more detail in future courses, and maybe a little bit more in my last lecture. Any other questions? Okay. Have a great weekend. See you Monday.